Hello, welcome to the Cobot Makerspace at the University of Nottingham. I'm Praminda Caleb Solly. I'm Professor of Embodied Intelligence. I lead the Cyber-Physical Health and Assistive Robotics Technologies Research Group. We are an interdisciplinary team working to develop intelligent robots to support health and well-being.
I'm Dr. Emily Crowe. I'm a research fellow in the School of Psychology with expertise in human sensory motor control and learning.
Hi, I'm Simon Carter-Green. I'm Technical Manager at the School of Computer Science, and I also work over here in the Cobot Makerspace. My role entails software engineering and supporting the robot-related research that we undertake here.
I'm Dominic Price. I'm a research fellow in Horizon Digital Economy Research and the Trustworthy Autonomous Systems Hub, and I'm also the lab manager for the Cobot Makerspace.
So to start off with, we're going to take you on a little tour of our facilities. And first up is our living lab. This is a fully instrumented smart home, and it simulates a studio apartment. In here, we're able to test different types of robot platforms, bringing in end users and trying out different scenarios of use. This room has got a motion capture system. You can see here, 8-camera Vicon system, which helps us to collect data regarding people's movements as they interact with the robots. And here's Jialin, she's our PhD student, working on developing a digital twin model of a robot and a human working together. And you can see she's set up with reflective markers. We're collecting lots of data with people. We've also got other types of sensors in this place, which allow us to monitor how people are using different furniture, etc. And you can see there, Jialin pointing to a smart home sensor, which then provides data to an assistive robot that can prompt people with everyday activities. And next up is our hospital ward simulation area. And here you can see another one of our PhD students, Angela, who is working with an intelligent mobility assistive device, the Leo Walker. And we use this to be able to collect data about people's balance and gait. And this is really helpful in analyzing how people change over time. And here you can see data from the handlebars, where you can see if people's balance changes over time. And we use machine learning algorithms to be able to track long-term conditions. We also have privacy-preserving, cost-effective sensors, such as this thermal imaging camera system, which is being developed for fall detection. And falls take place at night. This technology is helping identify when people fall so that a carer can be alerted, or a smart agent within the home can support the person. Over to you, Emily.
So our goal here at the Cobot Makerspace is to design healthcare technologies that involve collaboration between humans and robots. And this means that the human will always remain central to the solution. And today we're going to give you one demonstration of this. Mobility deficits are a very common consequence following injury or stroke, and can have a really negative impact on patients' mental health and well-being, because it often results in feelings of a loss of independence and a loss of agency. So one solution to this problem is to use sensing technologies that can detect the intact movements of patients and translate that into movements of a collaborative robot. And what this robot can do is then move around the house and perform various things for the patient. And what this means is that they can still maintain some of their independence despite having lost some of their mobility. So I will now pass over to Simon, who will talk us through this technology.
Thank you, Emily. So for this demonstration, I'm going to talk us through how we can use a pressure sensing seat map in order to control a mobile robot. So the seat map that we're using is a SensingTech seat map, and it has 256 pressure sensors embedded into the mat. Now, our algorithm takes the data from those pressure sensors and converts them into signals that the robot can use to actually navigate. Now, for this demonstration, we've actually got a maze built that we're going to navigate the robot round, and I'm going to basically give you a quick run through to show you how this works. So you can see on here now, I'm sat on the mat, and by shifting my weight around, I can control the robot. Now, on the screen, you should be able to see that there's a camera view from the robot, which shows you what the robot can actually see. So you can see as how we're navigating around the maze at the moment. And on the other side, you can see what we call a seat map, which is effectively a heat map generated from the data in the pressure sensing mat. Now, each of the sensors create a value of how much pressure is being put through them. And from these, we can build up a representation of where the distribution of weight is spread across the mat. Now, for our purposes, we convert that distribution into basically split it into quadrants and use the values of each quadrant to determine which way the robot should move. So we generate the kind of messages that the robot needs to understand the navigation.
So one thing that you might have noticed while Simon is driving is that the relationship between how Simon moves and how the robot moves changes depending on where that robot is within this maze. So when the robot's camera is facing away from Simon, like at the start of the maze, Simon and the robot essentially have the same viewpoint. And this means that Simon must shift his weight forwards to move the robot forwards, which is very intuitive and easy to do. In contrast, as you see now, whilst the robot comes around this corner, the robot's camera is actually facing towards Simon. So this means that Simon and the robot have different viewpoints. So now you'll see that Simon actually needs to move backwards to get that robot to the end of the maze and move the robot forwards. Now, this is harder and less intuitive, and so something that we're studying in terms of trying to design optimal control systems that are intuitive for the user.
What we'd like to now to do is bring somebody in who's never driven the robot using this control mechanism before. Would you like to come and take a seat? So if you'd like to introduce yourself.
Hi, my name is Gift. I'm a first-year PhD student here at the University of Nottingham.
Okay, and just to confirm, you've never used this control system to drive the robot?
Never, I haven't.
Brilliant. So what we'd like you to do is pretty much like I've just done. If you could just take a step in front of the seat map, sit down, and then obviously shift your weight around on the map to try and control the robot to see how far through the maze you can get.
Okay.
So all of a sudden, you can see right at the beginning, it's quite difficult initially to set off. And Gift is having to try and shift his weight now to try and avoid knocking any of our amazing ducks off of their stand. And we've got another minor clue. That's great. This is exactly what we like to demonstrate. So keep going. And a couple of the ducks have been just knocked there. And we're just trying to get around Ducky Corner, past the robot scrapyard. Oops. Brilliant. Okay, if you that's it, just lean back, that's the one. So you can see he's really actually having to put quite a bit of thought and effort into moving the weight distribution in order to navigate around the maze. And we're a little bit stuck on this duck corner. That's fine. So if you just give it a really good lean back, you should be able to get your...
I'm out of the maze.
Okay, sometimes if you stand up, it helps you just reset. So that's it. And then you can try sitting down and reverse up. Would you like me to pop you back inside?
Yes, please.
Yeah, no problems. Okay, and this is a really good example of how difficult it can be when you've never used it before. Okay.
Can I use my hand to essentially
if you wish to?
All right.
So what Gift's asking now is basically whether he can stabilize himself through the use of his hands. But yeah, go for it. Please feel free to do whatever you need to do to navigate around.
Oops.
Looks like you were going to take a shortcut there. Brilliant. Okay, so now we've got past this main bit, heading past Bingo, who's hanging out on the side there. We're going to just go past the Mindstorm, and we're coming to the cat roundabout, where hopefully we can get round the roundabout without clipping the cat. Lovely turn there. Spoke too soon. Oh, nice. Excellent. Okay, so yeah, brilliant. That's a really nice turn, and now Gift's controlling the robot with a bit more ease now, so it feels like he's starting to get the hang of the control system. Okay, and our time is up. Thank you. The gong has rung. So if you'd just like to take a seat back on there for me. So how did you find that?
At first, it felt like I didn't have particular control of the front and back movement. So while I was trying to navigate around, I noticed it kept moving forward, and then trying to stabilize my weight around was quite challenging because, I thought I was stabilizing my weight enough, maybe through the back, for instance, to perhaps decelerate. But it seemed maybe I needed to make maybe more motions or make it a little more obvious or so. So like making deliberate moves. But other than that, when I started using my hand, I felt I was able to maybe use strategic points behind behind my lap or my back, essentially, to navigate better. Hence, the less destruction there compared to here.
Excellent. That's a really good answer. Thank you very much for that, and thank you for participating in this and giving us a fantastic demonstration. Praminda.
Yes, so what you saw there was really interesting because you saw Gift who improved at the end, but when he was starting off, it wasn't very easy for him, and he was going around knocking a few things here and there. And that just goes to show you, because the system has been calibrated and developed for Simon, so Simon's weight, Simon's anatomy, and his patterns of movement and balance. And so we're looking to develop artificial neural network systems which are able to take that data, the sensor mapping data, and be able to generate better models that are individualized, personalized for particular people, for individuals. And so then we get this better mapping between the person who is using the control system, more intuitive, with controlling the robot. And extending that even further, the robot that you saw, the Locobot, has got a LiDAR sensor, and it's got its RGBD camera, which means that it can also do local obstacle avoidance and navigation. And this is particularly useful for somebody who might start off with being able to indicate to the system which direction they want to go in, and then the robot taking over and doing some of the lower level control of avoiding obstacles. And this shared control, shared autonomy model is really interesting to develop further, particularly in the research that we're doing here, which is developing assistive robots to support people with a range of different sensory, cognitive, and mobility impairments. Emily.
So with that, we would like to thank you for coming to look at our demo today. We hope that we've shown you the promise in the possibility of using this pressure sensing technology to guide a collaborative robot, and really think this could be used both inside and outside the home in its applications. Of course, we recognize that we are trying to develop a new control system, so there are still difficult things that we need to overcome. For example, how to make the mapping between the user's movements and the robot's movement intuitive, and also developing these personalized approaches to the calibration routines so that it's suited for each independent user.
Okay, so with that, we would love for you to ask us questions about our research and what you've seen here today.
Okay, so we've had a question come in from Daniel Watson, and I think probably Simon's going to be best placed to answer this. He asks, what kill switch mechanisms have been put in place for the robot in case the operator needs to shift weight for comfort instead of control?
Okay, now that really excellent question, and thank you for asking that. So at the moment, the main kill switch that we have is that the operator stands up, and what that does, it basically removes all of the signals from the pressure mat, so that the robot then basically gets a null signal and stops moving. But in terms of its how the operator can adjust themselves from a comfort perspective, it's a really good question, and we don't actually have anything built for that at that moment. We do have the ability to kill the script that runs in the background, which gives us an element of safety. But bearing in mind, this is a fairly low risk research grade kind of robot, and we're using it in a very controlled space. The safety aspects of that have been reduced and within a recommended kind of safe guideline. But it's something that actually I think we will probably take offline and actually have a look at about the shifting of comfort, and where we saw Gift actually using his hands to stabilize, and I suspect there was an element of improving his comfort whilst trying to control there. So yeah, really good question, and some opportunities I think off the back of that.
Yeah, definitely. This whole idea of sharing control between the system and the person is a really interesting research area. And as we start to use more physiological and implicit methods of controlling these systems, it becomes more and more important to conduct research in how to develop those control systems. So Emily, I think your research relates to this.
Yeah, so my research is really kind of focused on trying to make these new and novel control systems intuitive so that users can have a quick learning curve and be able to use them effectively quite quickly. So one area that I'm really interested in is the delays that are introduced by using robots. So if you imagine, as soon as you introduce a technology, I will move, but then there will be some delay until I see my movement shown in the robot, for example. So I'm particularly interested in how the delays that are introduced there, and either lengthening them or shortening them, has a direct influence on people's feelings of agency and whether they're really in control of this collaborative robot, because that's really important in terms of getting people to feel like these are good things to buy into and they are helpful things for us to use and engage with.
And we've actually been running some studies with robots to support dressing in my previous role in another project, iDress. And what was really interesting is we wanted to see whether we can model these unintended movements. So somebody sneezes or somebody gets distracted. How is that robot going to know that that person is distracted and it needs to stop? So again, an interesting open area of research for us to be working on.
Yeah, I think that's true. And in terms of being able to filter out the noise in the movement and detecting kind of the real intention of the user and what they want that robot to do and help them with. And I guess this kind of comes on to using various models and neural networks to train these models.
I think one of the things that we're interested in extending our research, I think building on from what you said, Simon, is how much the embodiment and the mechatronics will have an impact on the control systems that we develop and the mechanisms for supporting that, particularly when we start to look into working in more challenging environments of these systems, with these systems. So outdoors, people are using shared autonomy and teleoperation in situations for search and rescue, for example. So a teleoperator or a firefighter can be there controlling a system like this. So it's a really interesting way to bring in people from other disciplines to work with us to understand that relationship between how people learn and how they're able to then control the system.
Yeah, we've actually had another question from Russell Buchanan. Have you thought of other ways this could be used by humans, for example, while standing up or lying down?
Yes, indeed. There are lots of opportunities to be able to use that pressure seat mat as a control. And then we're also looking to see whether this can be used over a period of time to be able to look at people's changes. So if somebody was undergoing rehabilitation, they might be able to have better control. And then you could modify that system based on how well they were balancing. So yes.
Yeah, I think the standing up is a really nice example there, where you can use this pressure sensor, which gives this real-time feedback. So you can kind of train posture and any issues someone might be experiencing with that. So you can get this real-time feedback of, oh, you're not balanced and you're putting more weight on your right leg, for example. So it certainly has promise in a rehabilitation setting as well.
Yeah.
Okay.
And so I hope you will visit our website, the Chart Research Group website, the Cobot Maker website. We've got lots of opportunities for you to participate in events that we organize. We've also got a network, a health technologies robotics network. And if you look on our website, it's called Emergence. You can join up and stay involved with future events that we will be running here and organizing. Thank you.